Today, I'm going to introduce a new technique, COSBOS, or Color Sensor Based Occupancy Sensing. We are going to cover two parts, the Perturbation Modulated lighting and the occupancy estimation, including three methods. So, our target is to build a smart lighting system. We have a controllable LED and some sensors. Now we want to deliver the correct light in the space. By correct, we mean we want to minimize energy consumption and maximize human comfort. For example, if the room is empty, the lights should automatically turn off. If there are many people in the room, then the intensity of the light should be strong enough. We call this occupancy-sensitive lighting, and the sensor is the key to capture the occupancy information. So, what sensor shall we use? We may naturally think of cameras or other imaging devices, but do we really need a human-readable image? The answer is no. We just need to know which part of the room is occupied. We don't need to see your arms or your necks. If we can see, that is actually a problem, because someone else can hack into your camera network. You are exposed to the cameras, and we will have no privacy. This is the reason why we propose using color sensors. Color sensors only output a few numbers, thus it is safe, no privacy concern. Besides, these sensors can be very cheap. The problem is that there is really too little information from the readings of a single color sensor. However, we can use many sensors and make many measurements. When multiple sensors are distributed in the room, we can get the spatial information, and when multiple measurements are made under different lighting conditions, we get the spectral information. To demonstrate our ideas, we built a smart room. In this room, there are 12 color controllable LED fixtures in the ceiling, and we have 12 color sensors. These sensors can be installed anywhere. For each LED, we can specify the intensity of the RGB channels, and for each color sensor, the measurement is 4 numbers: red, blue, green, and white. If vector X is the input signal to the LEDs, and the vector Y is the output from the color sensors, we find that there is an affine relationship between X and Y. Well, if there is one mathematical equation you must know in our work, then this is the one. It is extremely important. The matrix A is called the light transport matrix, and this matrix is independent to the lighting condition. It only relies on the occupancy, thus it is a very good signature of the occupancy. If you are using different fixtures or different sensors, the affine relationship may not be true, but you can always calibrate your fixtures and sensors to make it true, because this equation is from optics and photometry. In the equation, there is an annoying B, which is the sensor response to the ambient light. We can eliminate B by adding a perturbation to the input and take the difference. Here x0 is called the base light, delta x is the perturbation, and delta y is the change in the sensor readings. If we apply n different perturbations, we get a linear system, y equals to ax. If we can make many measurements, for example, when we do a calibration for the empty room, the linear system is overdetermined, and we can solve it with a pseudo-inverse. However, in the runtime, we may not be able to make so many measurements because of the speed of sensors. Thus, our linear system is underdetermined. We can add extra constraints to get a unique solution. For example, we can assume the room is sparsely occupied, and we can do some low-rank recovery or sparse recovery. I am not going into the math details, but you can find the details in our papers. Remember that the matrix A is obtained by adding a perturbation onto the base light. So, what are the requirements for the perturbations? First, the perturbations should have rich variation. Also, the magnitude of the perturbations should not be too big and not too small. Here is some sensitivity analysis. The first row is the videos taken in the room with different magnitudes of perturbations. We can see when the magnitude is too large, the perturbations can be very annoying, even like a nightclub. When the magnitude is small, you will not see the perturbations. Well, if you think you see something from the video, that's image compression error. I assure you that when you actually stand in the room, and when the magnitude of perturbations is small, you will never see the perturbations. The second row is the sensor response to a sign perturbation in one LED channel. We can see that when the magnitude is too small, the sensor response will have some distortion. So this is actually a trade-off. The magnitude can't be too small and can't be too large. We have to pick a value in the middle. So this is a diagram of perturbation modulated lighting. The base light is the light that we want to deliver to the room, and the perturbations are modulated to the base light. There are two stages: sensing stage, where we add perturbations, and adjustment stage, where we change the base light according to the occupancy. This diagram shows the two alternating stages, sensing and adjustment. There is an occupancy sensing module and a control strategy module. The occupancy sensing module determines what is in the room, and the control strategy module decides what light should be delivered. We can compare the concept of perturbation modulation to the amplitude modulation in electronic communication. In AM, the low-frequency signal is encoded in a high-frequency carrier, and what we do is an inverse way. The perturbations are the signals, and they are the high-frequency components. After we have generated the perturbations, we want to put them in a good order. We want the light changes gradually, such that it is imperceptible. This is a graph problem, and can be solved by any algorithm for the traveling salesman problem. Now we have introduced the perturbation modulated lighting, and we can get the matrix A, or the difference between A and A0. What can we do with it? We propose three approaches to use A to estimate the occupancy. They are the machine learning approach, the light blockage model approach, and the light reflection model approach. Approach 1 is machine learning. We simply use the numbers in matrix A as the features to train support vector machine classifiers. To do this, we have to collect lots of training data and manually label the ground truth. We made 15 categories by dividing the room into 6 regions and place different number of human subjects in the room. The classification results are actually very promising. We get a 78% mean average precision, while the random guess is only about 8%. However, we must confess that this classification method has its limitations. In the real world, there are many categories, much more than we can include in the training data. And when we generalize the classifiers to new human subjects, the performance will drop. This is because of the overfitting. Machine learning algorithms can also learn some fake patterns from the training data. The second approach is 3D scene estimation. In this approach, we want to model the blockage of light. We first look at the matrix E. Each entry of E corresponds to a set of light paths from one fixture to one sensor, but not vice versa. This is because both the sensors and the fixtures have multiple channels. Thus, we aggregate the matrix E on different channels to get a matrix E hat. Now the entries of E hat to the fixture sensor pairs is a bijection. From one fixture to one sensor, there is one direct light path and numerous diffuse reflection paths. If one number in E hat is very large, then it means that the direct path corresponding to that fixture sensor pair is very likely blocked. When we know a light path is blocked, we do not know where exactly on the path is being blocked. But if there are many light paths being blocked, it is very likely that their intersection point is being occupied. Based on this intuition, we have our reconstruction algorithm. It is a weighted linear combination of Gaussian kernels. Each Gaussian kernel is computed using the point to 9 distance. The point is a position in the 3D space, and the 9 is the light path. The weight is just the entry of E hat. There is also a normalization term as the denominator. Our reconstruction algorithm is partially inspired by the inverse Radon transform. The volume is reconstructed by 9 integrals. The normalization term in our algorithm corresponds to the ramp filter in Radon transform, and the summation over light paths in our algorithm corresponds to the back projection in Radon transform. But our problem is very different from standard Radon transform problems. In Radon transform, the lines are densely sampled. For example, the sensor arrays can rotate and can scan slice by slice. But our sensors are fixed, and we only have a dozen of them. This makes our problem much more challenging. So this is the configuration of our experiments. The sensors are installed on the walls. This is the result when two people stand on the right-hand side of the room. We show the images captured by cameras, so you know what is the real occupancy scenario. But we clarify that the estimation did not use these images. All we use is color sensors. The bottom right is the reconstructed volume, and the bottom left is the summation of the volume over the z direction. You can compare it to the ground truth. This is the results when the subjects move to the middle, to the left. This is only one person. Move, 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 move. With only a few color sensors, the reconstruction result is so rough, you will not see the details. You will only roughly know where in the room is being occupied. This is actually a good thing, because this is all we need to know. Knowing more than needed will raise the privacy concern. Our reconstruction algorithm is written in C++. The direct algorithm is known, but we can accelerate this algorithm by pre-computing the point-to-line distances and Gaussian kernels, and hash them in memory. It takes about 2 seconds to render one volume. We can still make it even faster by parallel computing or using lower resolution. So, we have talked about the 3D scene estimation approach. It is good, but still has limitations. It is based on net blockage model. In some cases, this model will not work. For example, if there is furniture in the room, we cannot put the sensors on the walls. And if the room is too large, the occupants may not block many net paths. This is why we propose our third approach, which assumes the sensors are on the ceiling and is based on net reflection model. This is the geometrical optics and photometry of our model. For each fixture and each sensor, we consider a small patch on the floor and compute the number of photons that start from the fixture, be reflected by the patch, and finally arrive at the sensor. For each fixture and each sensor, we compute a reflection kernel, and our final confidence map of the occupancy is a weighted linear combination of the reflection kernels. The weights are the entries of E hat. These are the results for occupancy scenarios where there are two people in the room. This is only one person in the room. We can see that the confidence map is basically correct about where in the room is occupied. It is not as good as the 3D scene estimation results because the sensors are on the ceiling and we do not have the z direction information, but the results are still basically correct. So our conclusion: occupancy estimation can be done, but spatial resolution is no. This is because we are doing 2D or 3D estimation from 1D sensor output. This is an ill-posed problem. We can't get the information that is not there. If we use more sensors, the estimation results will improve, but more sensors means more money, and this is not really necessary. Here is a comparison between the three approaches. Each of them has its strengths and weaknesses. The current color sensor we are using is a commercial product. It is expensive and slow, thus it is only for experiments. For real applications, we need really fast and cheap sensors, and this is what we are building now. Thanks for watching this video. If you are interested in our work, you can visit our Project Wiki website. I am Quan Wang from RPI. Thank you.